Okay, partial ordering, section 9.6. Partial ordering is just simply a relation. Let's see what we mean by partial ordering. Orders mean we must order the element in some set some way, saying some element is bigger than or smaller than the other. Sometimes we can do this comparison and sometimes we cannot. Now smaller or greater here will have different meanings than the usual meanings that we are used to, and this is what we are going to learn today. So we will call a relation R, we will on a set S, it will be called partial ordering or partial order. If it is symmetric and reflexive and antisymmetric and transitive. Simply, we know these properties. We know that a relation which is symmetric, reflexive, and symmetric, and transitive is called equivalence relation. This is close to it, but replacing the symmetric with antisymmetric. So, a relation which is reflexive, antisymmetric, and transitive would be called partial order. Remember, the antisymmetric property does not allow two different elements to relate to each other in both ways. Does not allow two different elements to relate to each other in both ways. If this happens for two elements, then they must be the same element. And this will enable us to do comparison between elements. We will see how these things come out. Okay, so this is the how we denote a partial order on a set S. R is the partial order and S is the set. Now S together with a partial order is called partially ordered set. Partially ordered set. And this is the notation again. I would like to write it here. It is S, R. S is the set, R is the relation. And it is abbreviated POSET, partially ordered set. This is a very important concept in mathematics and computer science. Okay, so a partially ordered set is a set with a relation which is reflexive, antisymmetric, and transitive. So it's easy for us to see examples because we already know about these properties of relations. So let's see this example. Here we'll start with a relation which is greater than or equal. So we will relate to integers on the set of integers by greater than or equal. So we are saying here the greater than or equal relation is a partial ordering, and we need to prove that. So usually you will be given a relation and you are asked to prove whether it is a partial ordering or not. Just go and prove the three properties we have seen. Reflexive. Now, is this relation reflexive? Yes, it is, because every element is greater than or equal to itself. Is it antisymmetric? Antisymmetric. If A is greater than B, which means A related to B, and B related to A, which means B is greater than or equal A, and we have already A greater than or equal B, then we must have these two elements are the same. So this is antisymmetric has been achieved. Transitive. It is easy to see this property. If A is greater than or equal B and B is greater than or equal C, then for sure A is greater than or equal C. So it follows that this is a partially ordering set, and here it is Z with greater than or equal relation is a POSET, partial ordering or partially ordered set. Okay. Now another example on the set of positive integer, the divisibility relation. The divisibility relation, this is how we denote it, is a partial ordering in the set of positive integers. Right? We need to prove that. Reflexive, so I will do it for a quick. This is true because A divides itself for every A on the set of integers. Good. Antisymmetric. If A divides B and B divides A, then for sure A and B are the same. Transitive. Actually, I was planning to leave this to you, all of it, all these properties, and then prove it is indeed transitive. So I want to stop at this example now and speak a little about it. Now again, this example says that the set of positive integers with divisibility is, this is divisibility, let me highlight it, is a poset. And to confirm that it is partial ordered set. Okay, what do I want from example before I keep moving? It says partial order. Notice this word. It is partial order. Order means arranging. Let's take it in the intuitive thinking, intuitive meaning of word order. Order means we want to put elements ordered some way. Okay? Now, sometimes we cannot put all elements of the set ordered some way because the order we are making belongs to some relation. We cannot order all elements because not all elements are related. This is why we call it partial order. Partial means some elements are related to each other and some elements are not related to each other. And here we go, the divisibility. 2 is related to 6 because 2 divides 6. But 4 is not related to 6 because 4 does not divide 6. 5 does not divide 6, so 5 is not related to 6. 7 does not divide 9, so 7 is not related to 9. But 3 divides 9, so 3 is related to 9. So if I want just to cheat from what we want to do in a little while, I will go say, okay, 2 and 3, I will do this because they divide 6. Okay? And now 3 will divide 9. And 2 will divide 8. Now where's 4? 4 divide who? Divides 8. Okay, so where's 5? So this is partial ordering. So if you see here, 3 is not related to 8. 4 is not related to 6. 2 is not related to 9. So partially ordering, that means some elements are related and some are not. So we can do ordering in some way partially. So we call it partial ordering. And this is another example now of partial orders, which is the power set. Now we know in a power set, giving S a set S. Now take the power set P of S. So we imagine that we have S with n elements. Take the power set, which means all subsets of S. Now take two subsets. One of them might be contained in the other, and it might not. So if you take any two pair of elements of the power sets, you might find one of them is contained in the other, and it might not be. So this is partial ordering. So the inclusion relation is partial ordering. Okay, it is reflexive because A is contained in itself for every A. It is antisymmetric. If A is contained in B and B is contained in A, then A and B are the same. And clearly it is transitive, as we see here. So this is the containment, the inclusion relation, we call the inclusion relation, is partially ordering in the power set. And I would like you to go and make some fun. Take S to be 1, 2, 3, 4, and make a diagram that we will do it in a while, but I would like to do some of them here. Like I would say 1 and 2 this is contained in 1, 2, 3, and 1 and 4 is so I will do this, which means representing the relation 1, 3, 4. So this is contained in this is contained in that, and each one of these will be contained in S, but this is not contained in this, and this is not contained in that. So this is a very interesting example, and it is the very intuitive example of partially ordering. For myself, when I was a student, when I learned this, the partially ordered set, I keep forgetting this because I keep mixing between the definition of partially ordered and equivalence relation. They look like both of them are symmetric. I'm talking about equivalence relation and partially order again. Both of them are symmetric. Both of them are transitive. One of them is let me fix what I said. The equivalence relation and partial order, both of them are reflexive. I said symmetric. Both of them are reflexive, and both of them are transitive. Okay, but one of them is symmetric and the other is not. So I kept mixing between which one is the symmetric, which one is the anti-symmetric. One of them is anti-symmetric, one of them is symmetric. I said not. I mean, I need to be specific. One of them is symmetric and the other is anti-symmetric. I should not say not symmetric. This is different. Not symmetric is different than anti-symmetric. So I kept mixing which one has the symmetrical property and which one has the anti-symmetrical property. So I kept mixing this a lot of times. So using this example here, why I am saying this at this moment? Because this example will always remind me what a partially ordered set is. When I forget, okay, partially ordered set, how I remember the axioms of it, the three properties. Then I say, okay, the partially ordered set of the power set of a set. I know it is reflexive and transitive, and it is antisymmetric. If A is contained in B and B contained in A, then they are equal. Okay, now I can remember the definition. That this is what I'm saying at the end. I can remember the definition of partially ordered sets when I have this example in mind, the power set of a given set. Okay? Now, we will adopt annotation for partially ordered sets. We will use this notation. I just will rewrite it this way. It looks like less than or equal, but it is not. It is a generalization. So it is slanted. So A, we will read it less than or equal, but we will not really mean a less than or equal, the one we know between integers, because this can be between subsets. It might refer to inclusion. It might refer to division. Okay, so we will say A less than or equal B is to denote. So this is a new notation. Okay, I will write it here. It is less than or equal B because A is related to B in R. Okay, but we will reserve this notation not for any relation, just for relation that gives partially ordered set, for relation that makes partially ordered set sets. Okay, and we will write it this way. Now, when two elements A and B are elements of the set, it is not necessary either A is less than or equal B or B is less than or equal A. We just have seen that, like 3 and 6. Okay, 3 divides 6. Okay, so we will write 3 related to 6 this way. Okay, but choose 4 and 6, and then 4 is not related to 6 under division. And we have seen also 1 and 4 is not related to 1 and 2 and 3. So it says here, if you take two arbitrary elements A and B from this set, the partially ordered set, then it is not necessarily that one of them must be related to the other. This is why we are calling it partial. This is why we are calling them partial order, because not all elements, not any arbitrary, not necessarily that any pair of elements are related to each other. They might not, they might be and might not. So that's why we call it partial. In a little while, we will see totally ordered. Totally ordered. That means every two elements must be related to each other according to that relation. So we can't decide which one is bigger, which one is smaller. That's when we get to what we will call totally ordered. Now we are working in partially ordered sets. Okay? Now, here it says, for instance, it says 1 and 2 is not related to 1 and 3 because 1 and 2 is not contained in 1 and 3. Here is the... now, in this instance, with with this notation means for us here containment. In this instance here, this notation means divisibility. Okay, so 2 is not related to 3, 3 is not related to 2, and we see that. Okay, now we have seen two elements might be related or not according to the partial order. When they are related, then we will say they are comparable. We can compare which one is less than or equal the other. And less than or equal here between quotation marks, less than or equal means the relation we are talking about. It might be divisibility or containment and so on. So some elements might not be related and some other might be related, and we will call the ones that are related, we will call them comparable. So two elements, A and B, in a partially ordered set are called comparable if either A is less than or equal B or B is less than or equal A. In this example, in the divisibility relation, 3 and 9 are comparable because 3 divides 9. But 5 and 7 are incomparable because neither 5 divides 7 nor 7 divides 5. Okay, now two elements may be incomparable. When two elements may be incomparable, then the relation is called partially ordering. So this is a rephrasing of what I emphasized on. It says here, if we find two elements that cannot be compared, they are incomparable, then we will say this is a partial order. Two elements that are not comparable are enough to say the relation is partially order, is a partial order, which means there are some elements that are not comparable, which means that are incomparable. Now here it says when every two elements in the set are comparable, then the relation is called total ordering. This is natural to say. So total ordering is a relation R on a set S where every two elements in that S are related by R. So we can say total ordering. So if you want to order the element of S according to the relation of R, we can order them all together. And every two of them will be related. We can decide, given any two elements, we can decide which one comes first and which one comes after. That's a total ordering. So this is different than partial ordering. Partial ordering, we might have two elements that we don't know which one comes first and which one comes after. Okay. Now this is the definition of total ordering. Now, okay, if S is a partial order poset and every two elements are comparable, then S is called total ordering or linearly order, and this relation will be called linearly order. For example, let's see here, the less than or equal, the one we know here, we mean by this example, this notation now means the less than or equal, the usual one we know between integers. It is totally ordering, okay, because either for every two integers, given two integers a and b, one of them must be less than or equal the other. So it's either a is less than or equal b or b is less than or equal a. Now let's see why we call it linear ordering. We can demonstrate the relation in this example. Look, we can say, okay, it's 1 and it is less than 2, so I can make this line here representing that 1 is related to 2 and 1 is less than or equal to 2 is less than or equal to 3 3 is less than or equal 4, 4 is less than or equal 5, and so on. So when I demonstrate, this is 0 here, -1 here, when I demonstrate the relation using what we call later in a little while hash diagrams, then I can put them in order in one line. In one line. That's why we call it linearly ordered. Every two elements are related to each other. Okay. Now we have seen also that the partially ordered set, the positive integers with the division, is not totally ordered simply because 5 and 7 are not comparable, are incomparable, and there are infinitely many pairs of integers in this situation that are not comparable or that are incomparable. Lexicographical ordering. This shows how to do comparison between ordered pairs or 3 tuples or n tuples in general. And this way of ordering, lexicographical order, is the one that are used in dictionary. When you have a word, English word, say, and you find it in the dictionary, and then you will find the words arranged in the dictionary in the following order. First, it goes to the first letter that comes in the word, and then it lists all the words that comes with the first letter together, and then the second thing, it will go and look at the second letter, and it lists all elements that have the same first and second letter together, and then it goes to the third letter, and so on. This is what we call lexicographical ordering. And let's understand it, how it works in the ordered pairs. But let me say that if I ask about less than or equal, the natural ones we know about integers, given any two integers, you can say which one is less than the other, right? Now, what if I ask you to decide which one is bigger, 1 and 9, 2 and 3? Can you decide which one is bigger? We cannot. If you want to say, okay, I go to the first component and this one is smaller than this, but I will say, what about the second component? 9 is greater than 3. Okay, so we need to force some ordering on such situations, which we call lexicographical ordering, and it will tell you how to do that. Okay, now we start with two partially ordered sets. Okay, and I want you to pay attention here that we are bringing a set we call A1. It is just set, and it has its own partial order in there, and another set A2 with its own partial order in there. Okay, now lexicographical ordering would say, okay, I want to define an order on the cross product of A1 cross A2 by saying that we will say that A1, A2, this ordered pair here, is less than the other ordered pair, less than when? If either the first component and the first component in both ordered pairs. So I will go and compare the first component here and here. If I find one of them is less than the other, then I will say, okay, the ordered pair that has the smaller first coordinate is smaller than the other ordered pair. Okay, if I find them the same, if I find the first component or coordinate of one of the ordered pairs to be smaller than the first component of the other ordered pair, then I will say the first ordered pair is smaller than the other. But we might have them equal. We might have that these two components, the first component in each ordered pair, to be equal. What we do? Then we move and check to see what happens to the second coordinate here. And we will, if we find the second coordinate is smaller, then that ordered pair will be smaller. And now notice here, when we compared second coordinate, we used the relation that's coming from A2. When we compared first coordinates, we use the relation that's coming from A1. Okay, so let's see here. We will say 3, 5 is less than 8, 4 because first component here is less than first component here, and then we are done. Now let's go to the one after. First component here is the same as first component here. So what we do next? We go to the second component. So first component are the same. So we go to the second component now, which is we compare 9 and 11, and we find that 9 is less than 11. Then we will say this ordered pair is less than that ordered pair. Okay? Again, we can compare these two 4 tuple. Okay. Now we go to the first coordinate. They are the same. Okay, so we cannot decide. Then we go to the second coordinate. They are the same. Then we cannot decide. But look what happened. We went to the third coordinate. We found this to be 3. And third coordinate here is 4. So we will say that this n-tuple is less than the one to the left. Right? Okay. So this is what it is called lexicographical ordering. We are interested in the definition of this ordering only, and there are some exercises ask you to do such comparisons. Okay, now we will go ahead.
Should the relation only be less than, or can the relation be greater than or division?
Yes, it can be the relation on the first coordinate. It can be some relation which is different the relation in the second coordinate, which might be also different the relation of the third coordinate, and so on. But here we used the relation which is less than the one we know, the natural one we know between integers, and we have taken it at that direct and that easy. And I believe in the exercises it will be the same. And for now we are interested in these cases only for lexicographical ordering. And we will see later, we will go to exercises and see if some different relations according to coordinates are defined. We will look at them later. Okay. Now let's go to Hasse diagrams. These are just to represent how elements are related to each other, and I have already used them because they are very helpful. Like consider the directed graph for the partially ordering set. Partial ordering now A is related to B if A is less than or equal B. Actually this is total ordering, but we still can call it partial ordering. Okay, in the set 1, 2, 4. Okay, look at the left. What it says, okay, 1 is related to itself, 2 is related to itself, and so on. 3 related to itself, 4 related to itself. 1 is related to 3, and it is related to 2, and it is related to 4. This is too much complication, too much lines. So we can just at the first step say, okay, we want to get rid of these loops here. Just make nodes, which means now we understand now taking these nodes here means okay, we know that there are loops at these nodes here. And now we again say, okay, let's get rid of these lines here, like from 1 to 4. I want to get rid of it. Why? Because if I go from 1 to 2, and 2 goes from 2 is less than 3, 1 is less than 2, and 2 is less than 3, then I know is 1 is less than 3 because we have partial ordering, because it is transitive. And 3 is less than 4, so I will say, okay, as long as I'm having this line, 1 is going to 2, 2 goes to 3, 3 goes to 4, that means I can go from 1 to 4, and from 1 to 3, just following the lines. So this is the Hasse diagram, and this is better than these two things here. So we will adopt the abbreviated, the cleaner diagram that represents relation, and this is what we mean by Hasse diagram. Okay, let's look for more examples for the Hasse diagram here. Okay, draw the Hasse diagram representing the partial ordering of this sets. Now the partial ordering, it divides. This is a partial ordering. This is not total ordering. So 1 divides 2 and 1 divides 3. 1 divides every one of them. So this is very hassle to write them 1 1 1 2, and then we keep going all the way 1 2 12, and then 2 will divide 4 and 2 will divide 6. This is so much hassle. We can arrange them in ordered pairs, but you can directly make such a graph. Okay, so 1 is connected to any other integers, like 1 to 8. We just follow this path to go from 1 to 8 all the way. We reach 1 to 8. That means I have 1 8 represented. So 1 8 is represented in this relation because I can move from 1 to 8 following the lines. And same thing for 1 and any other integer. Now let me erase that. Actually, I want this to be clean. What's about 2? 2 is related to 6 and is related to 4, and it is related to 12 this way, and it is related to 8 that way. What about 3? 3 is related to 6 and it is related to 12, but it is not related to 8. I cannot find a path that takes me from 3 to 8. I cannot find the path. And 4 is not related to 6. I cannot find the path. But 4 is related to 12. Okay? Let me make that diagram clean again. And what else? 6 is not related to 8, so I cannot find the path. Did I say that? Okay? But it is related to 12. And so on. So I believe you got the idea. This diagram is a very interesting, very nice, very smart way to represent partial ordering. Okay, when I represented a little while ago the relation of less than or equal on the integer, they came out to be one line that was total ordering, which we call linear ordering. This is not linear because the representation did not come in a line, or because there are elements that are not comparable. Okay, so let's make another Hasse diagram. I already tried to do this. We will do it again with this example. Now S is ABC, and the partial ordering here on the power set of S, not on S itself, but on the power set. And the partial ordering is 2 sets A is related to another subset B if A is contained in B. So let's see. Phi is contained in any subset. Here we go. All subsets, so maybe you need to see the power set consists of phi, A. So all subsets, the power set consists of all subsets of S, AB, AC, and so on. You know them all. Okay? Phi is contained in any of them. So you can start at phi and move to any other set. Like for example, to move here, phi is contained in this one here. Okay, I can move it. Phi is contained in B, and B is contained in this one. Or I can come this way. And phi is contained in this set also. So I can come this way to it. So that means I can relate phi to this set. Or phi is contained in this set here. So I can go this way and this way and this way, which means phi is contained in C, but C is contained in AC, and AC is contained in ABC. Okay, now you can see any relation here is any two subsets related to each other are connected by some line. For example, the subset consisting of A is contained in AB. You see that? And the set B also, let me say the set B is contained in this one. Okay, the set C is contained in AC, or the set C here is contained in ABC, so because it is contained in BC, and BC is contained in ABC. So I think you got the idea. Now, when you make such a diagram, try never to miss any line representing two elements that are related to each other. Okay? So good. We learned about partial ordering, which means some elements are less than or equal others. And now again, less than or equal here means not necessarily means that less than or equal in the usual sense that we know between integers, but it might represent conclusion, it might represent division, it might represent any relation. The less than or equal here, again, I want to emphasize it, this notation here, it refers to a relation. This is a relation, a partial order relation. Okay, so when we see that as a partial order relation, then that will say less than or equal. Okay, now an element E will be called maximal. Here it is not maximum, it is maximal. Why? In opposite S, we will see why. If there is no B in S such that B is greater than A. So A is called maximal. I'm not saying if it is the biggest one in S. No, that is maximum. The biggest one is maximum. Here I'm saying maximal with A and L, which means no one is bigger than it. I'm not saying it is bigger than everyone else. No, I'm saying there is no element above A. There is no element above A. So it is maximal. Okay? And also it will be called minimal. An element will be called minimal in the partially ordered set if there is no element less than it, less than A. So I'm not saying A is the smaller element in S. No, I'm not saying that because that would mean maximum. I'm saying maximal, which means there is no element smaller than it. There is no element smaller than it. Okay. Now, to make this definition clear, we must go to examples. But here it says minimal and maximal. Minimal and maximal elements are the top. The maximal is in the tops. So when we make hash diagrams, we might have different tops. Each one of these top is a maximal. So we may have more than one maximal element and also more than one minimal element. So the top is for maximal and the bottoms are for minimal. So this is an example. So the poset, let's take the poset that consists of the set 2, 4. So this is the poset. And the division here is the relation. And this is the set S. This is the set S. Okay. Now, the hash diagram of that is, here we go, 2 divides 10, 4, and 20, and 12, okay? And 5 divides 10, and it divides 20, it divides 25, and it does not divide 4 and or 12 or 2. Now, 2 divides 10 and 20, and 2 divides 4, 2 divides 12, and 4 divides 12, 4 divides 20, but 4 does not divide 10. So we have this hash diagram. Let me clean it. Now we can see that this is a minimal because there is no element in the set S that is less than it. There is no element that divides to here the set, because remember the divides here is the relation. And 5 another minimal element. And also we go to 12. Look at the set. We are talking about the set S. Is there an element in the set S for which 2 divides, which is divisible by 12? Sorry, not 2. No. So 12 is maximal. Same thing for 20. There's no element for which 20 divides. Is a factor or divisor. So this is maximal, and also 25 is maximal. Okay, 4 and 10 are not neither minimal nor maximal. Okay, now we will also talk about greatest, which is the maximum in your understanding from calculus. Okay, but we don't want to see here maximum, because we might confuse that with maximal, the one we already know. So we will call the greatest element just the greatest element. An element in A here, it is called the greatest element of S if A is greater than any other element in S. A must be greater than any other element in S. Must be, to say it is the greatest. And we will say A is the smallest, the least element if A is less than every other element. Every other element. We will see from this diagram. Now, here A, this one, is less than B and C and D, because the graph says that A is related to B, related to C, and related to D. Okay? So this is the least element. Now, the least elements, they may exist and may not exist. And whenever they exist, they are unique. There is only one least element, and there is only one greatest element. But when we talked about maximal and minimal element, we might have more than one maximal element and more than one minimal element, as we have seen in the examples above. Let's keep going. Now, concerning this graph here, do we have a greatest element? Greatest element means it is greater than any other element. Now, if we think to choose B, B is not greater than C. So we cannot say B is greatest element. And same thing for C. C is not greater than B or D. D is not greater than C or B. So no greatest element. No greatest element here. What about this one here? Can we say this is okay? Do we have a least element? A least element here? If we think about A, look at B. If we want to say a least element, that means it is less than any other element. Is A less than B? No. Is B less than A? No, they are not related. So there is no least element. No least element. What about greatest element? Do we have a greatest element here? Yeah, I'm waiting answer. No. No greatest element. Greatest element. Oops. Okay. What's about this one here? Do we have the third digraph? Do we have the third digraph here? Do we have a least element? Again here, no least element. Do we have a greatest element? And this is one, the greatest element. What about this, the fourth one? Do we have a least and the greatest? We can see this is the least element, and this is the greatest element. Okay, now again, let me say it again. The greatest element, it may or may not exist. When it exists, it is one only. We cannot allow more than one greatest element. At the same time, maximal element, there might be many maximal elements. Same thing applies for least element. The least element may or may not exist. Okay, whenever it exists, it is unique, only one. This is not the case for minimal element. Minimal element always exist, and they might be There might be many of them. Okay. And there are more examples for minimal and maximal element. Let's see the least element and the poset. The least element in the partially ordered set, P of S. P of S is the power set, and the relation is containment. So the least element is the power set, because the power set is contained in any other, the empty set. I'm sorry, I'm saying the power set. The empty set is contained in any other set. This is the definition of the least element, is less than any other element. Okay. While the greatest element in this poset is the set S itself. Now, if we want to demonstrate that, we will say S, and then we take subset out of this, and then this will go for more subset, and we keep going, and at the end, all of them will meet at phi, because phi will be contained in any one of them, and S will contain every one of them. S will contain every subset. That means S contained every element in the power set. So S is the greatest. Phi is contained in every subset. So phi is less than every element of the power set. So phi is the least. Okay. Now another example here. The integer 1 is the least in the poset, the positive integer with a division. It is normal because 1 is less than 2, divides 2, and 2, now we can say 2 divides 4, 2 divides 6, and where is 3? 1 divides 3, 3 divides 6, 9, and then 8 is somewhere here, and so on. And 6 and 8 will meet at 12, and so on. But we know now this is the least element in this poset. But there is no greatest element, because the greatest element here means the integer, the positive integer, that is divisible by any other integer. What is it? It does not exist. You may say infinity, does not apply, the definition does not apply. Okay. Now, let's go to more definitions here, which is important, which talks about upper bound and lower bound. Okay. Now, we start this way. If U is an element of S, okay, such that U is greater than any element A in some subset A, then U is upper bound of A. What does that mean? Okay. Let's make it clear. We want to say here, this element U is an upper bound of a subset A. What's happening? We have a set S, okay? And there's a partial order there. Say this is a set S, and there's a partial order. It has some partial order. Okay? Now, we are saying, assume that we have a subset, capital A in S, okay? Now, we will say that an element U is upper bound for A if it is greater than every element in A, okay? So this is upper bound. It bounded, U bounds A from above because it is greater than any element in A. So I don't know how to demonstrate it here. It might be inside A and it might not be inside A. Okay? So maybe I will say, okay, it is here and it is greater than any other element here. It might be inside A. Okay? So if I want to do another digraph, so I will say this is S and this is capital A and this is U here, and it is bigger than any other element in U. So in A, sorry. So this is a good demonstration that might help you to visualize the definition. So U is an upper bound of a subset. So we are choosing subset from S. We are using subset capital A. U is upper bound of A if it is bigger than every element in A. Okay. Now we might have more than upper bound of the capital A. We might have U1, we might have another U2, which is also an upper bound of A, and we might have U3, which is also another upper bound of A, and the same thing applies here. This is U1, this is U2, and we might have U3. Some of them might be inside the capital A or not. So we might have more than upper bound. This is natural. We are saying an element which is greater than all elements in A. There might be another element doing the same thing, and one more. Now, if we take the smallest one, the smallest upper bound, which we will call the least upper bound. Now, this is the idea here. The least upper bound of a set A, we will call it X. If X is an upper bound, which is less than every other upper bound. Okay? So we might say, oh, okay, here, U2, maybe I will demonstrate it. Let me go back here. This is A, and I might find some element here, which is X. Let me write it X, which is also an upper bound of A, but maybe X is less than U, and it is less than U1 and U2 and less than U3. So I will say, okay, this is X is the least upper bound, So the least upper bound of a subset A is an upper bound of A, but it is the least upper bound. It is less than, or smaller than every other upper bound. Okay? Now, same thing goes for lower bound. If I want to make demonstration now, L is called an upper bound of A if L is smaller than any other element in A. So let me demonstrate that in this diagram here. So let's say this is S. Here, this is S now. And we have, okay, this is A somehow. This is the set A. Okay. Now we are assuming that we have some L. What's the matter with that L? It is smaller than, so let's assume the elements in here, smaller than any element in A. So we will call it upper bound, okay? We might have some other elements that do the same. So if we call this L1 and this L2, we might have different lower bound. Did I say upper? We might have one more which might be inside A3, which is smaller than any element in A. So all of them are lower bound, L1, L2, L3. We might find now another upper bound which we call Y, which is smaller than any element in A. So it is a lower bound of A, but is also smaller than any other lower bound. So here we go. Y is called no, I fixed that. I need to fix that. Sorry. I need to fix my diagram. Is the greatest. I need to fix my diagram. This is so bad. Okay. Now we will define what we mean by a lower bound of a subset A. So we will call an element a lower bound of A. So let's make a diagram of what the definition we are explaining. So assume we have a set S here. This is a set S, okay? And assume we have a subset A inside S. Then we will say, and assume we have elements here. We will say that an element L is a lower bound if it is smaller than all elements of A. This is what we are saying here. An element L of S, if it is smaller than all elements in A, then L is called a lower bound. L might be inside the set. So let me say this is a lower bound. Now I might choose another lower bound which is inside the set. Let me call it L2, and for sure it must be less than greater than L1, and then L2 is another lower bound if it is lower than any smaller than any element in S, okay? And we might have another lower bound, say L3 somewhere, L3, and so on. Now, we will go here and see what is the greatest lower bound. The greatest lower bound, we call it Y. If it is a lower bound, so I will demonstrate it somewhere. So I will demonstrate Y here. It is a lower bound of A, so it is smaller than any other element in A. But it is greater than any other lower bound. It is greater than any other lower bound. So this is my way to try to make it a clear picture. This is unfortunately not very clear picture, but we will see that Y is the greatest lower bound if it is a lower bound of A, and it is the greatest one, and it is greater than any other lower bound. Okay, now let's apply these in the following pictures. Now in this example, let us find lower bound and upper bound. So giving this is the same figure, the Hasid diagram, but I copied twice because I will write a lot on them. Let's take the set A. This is the set A, consists of A, B, C. Okay, this is the set A. Now we want to find upper bounds of A, upper bounds. So let me find where are A, B, C. This is A, this is B, and this is C. Now to find upper bounds, all of them, I need to find all elements that are for which every one of them is greater than A and B and C. Now if we look at E here, E is greater than C and A and B. F will do the same thing, and G and H. That's why, because I can go from B to E and B to any other one of these. Same thing, I can go from A to any one of these, and from C to any one of these. But I will not take G because I cannot go from C to G. I cannot do that. So the upper bounds of the set ABC are E, F, G, and H. And here they are. Here they are. What is the lower bound of this set A, B, and C? I want to take the element which is less than any other element in the set. So I will just go for A because it is less than B, it is less than C. But I will not choose B because it is not less than C, or C because it is not less than B. So the lower bound of this set is only A. The lower bound of this set is only A. Now let's choose another set, which is, and make that in the diagram to the right. A, C, D, and F. Where are they? This is A, this is C, where is D? This is D, and this is F. We want to find the upper bounds. Upper bounds. Okay, I will say, okay, can I take G because it is greater than D, but it is not greater than F. I cannot go from F to G, so I will not take G. Okay, can I take E? It is greater than A and C, but it is not greater than. I cannot take E. Can I take G and H? of the set. هذه الست نتكلم عنها اللي هي G و H. Okay, the greatest lower bound. Is it there? These elements that have square on them, is there a greatest one? Is there an element which is the greatest one? Anybody tell me it is F? Thank you, Modda. Is F. Okay. This is the greatest lower bound of the set G and H. Okay, the greatest lower bound. Okay, we cannot ask about the lowest upper bound of G and H because there is no upper bounds for G and H. Okay, good. Now let's go to the following set, but before I go I need to erase the things in this diagram so that we use it again. Okay, now let's take the set to be B, D, and G. Okay, B, D, and G. Come on, please. B, D, and G. Okay, B, where is B? This is B, this is D, and where is G? This is G. Okay, we want to see where are the upper bounds in green. The upper bounds of B, D, and G, we can decide it is H only. We cannot take F because it's not related to G. We cannot take J because it's not related to G. Because it's not related here and not related here. Okay. And we can okay, good. Now the upper bound is, let me erase that, is H, and if we, the whiteboard is not answering me. Again, the upper bounds of B, D, and G are H because it is greater than any other element in B, D, and G, and also G because it is greater than or equal any other element in B, D, and G. So these are the upper bound. And now if you want to talk about the least upper bound of this set, so in green we have G and H to be upper bounds, and the least one is clearly is G. Okay, okay. Now let's take the lower bounds of the same set, B, D, and G. What is the lower bound? It consists of A because it is less than or equal to any other element, and B. So these are the lower bounds of this set. Now the greatest lower bound of this set is B because B is greater than A. Okay, because B is greater than A. So here we talked about the greatest lower bound and the least upper bound. Okay. Now, what if I want to ask you about the greatest element of this partially ordered set and the lowest element? The greatest element and the lowest element. So greatest element and lowest element has nothing to do with choosing subsets from the whole set S. They are greatest element or least elements with respect to the whole set S. So can you answer me now, what is the, let us start, what is the greatest element in this set? So if I want to go now, just erase all that here. Now tell me what is the greatest element if it exists, and the least element of this set. Okay, who tells me? What is the greatest element of this partially ordered set? So I'm talking now about the whole set, this partially ordered set. So this partially ordered set has no greatest element, has no greatest element. Okay, but does it have there is G? Yes, because H is not greater than G. We say here H and H is not greater than G. This is not true. Okay, what about the least element? The least element. What do we have a least element here? Which is A as its least element. Okay, this is what my brain was thinking when I talked about greatest lower bound and this element. Okay, so let's move now to example. Okay, find the greatest lower bound and the least upper bound. So usually we will say greatest lower bound of some set A, and I did not write dissertation, and least upper bound of some set A. Now, the partially ordered set here is the set of all positive integers with partial order division, and the set here for this instance, let's choose this to be A, and name this set to be B. So tell me what is the greatest lower bound of A. Does it exist? Okay, sorry. The greatest lower bound of A. What they are? What is it? The greatest lower bound of A. Can anyone tell me? If we try to make them as Hasse diagrams, we will say, okay, 3 divides 9 and 3 divides 12. Okay, this is A, but now we know that 1 divides 3. Okay, and what else divides 3? Nothing. Okay, and in between 3 and 12 we have 6 in here, and then we have 12. Okay, in above 12, what is greater than 12 and 9 at the same time, which means what is the least common multiple of 12 and 9, and it is what? 36. Okay, now you can tell me what is the greatest lower bound and what is the least upper bound of A, and you can simply say this is the greatest lower bound is the greatest common divisor of A, and the least upper bound is the least common multiple of A, and just you can decide what is the greatest common divisor of these integers, which is greatest common divisor is 3 and the least common multiple is 36. Now when you are given set of integers with division relation, then you can quickly decide what is the greatest lower bound, which is the greatest lower bound, which is the greatest common divisor of elements of B, and you can find it at 1. And what is the least upper bound of A is the same as the least common multiple, sorry, this is B, of the elements in B, and the least common multiple comes out to be, if you do it, 20. Okay, or you do a Hasse diagram of it, but if the partial order set is the set of positive integers, and the relation is addition, then just least upper bound is the least common multiple, and the greatest lower bound is the greatest common divisor. Okay, now the last part of this lecture are lattices. What do we mean by a lattice? It is a partially ordered set in which every pair of elements has both least upper bound and greatest lower bound. We have seen that some sets may not have least upper bound, They have upper bounds, but they may not have least upper bound. And you might be asked which, given a set of partially ordered sets, and then I give you 4 or 5 sets choices, and then I will ask you which of them does not have a least upper bound, which of them does not have a greatest lower bound, okay, or which of them do have a least upper bound. Or I will give you a partially ordered set and an element. I will then ask, this element is a least upper bound for which of the following sets, or it is a greatest lower bound for which of the following sets. Okay, now but here we are talking about lattices. So as what I was saying, some sets may not do have least upper bound or greatest lower bound, but we will have a special case, a special kind of partial order set. If we find that every 2 elements have least upper bound from above and greatest lower bound, every 2 elements, if we force every pair of elements, A and B, to have least upper bound of them to exist somewhere. They might be directly connected or not directly, and we force them to have a greatest lower bound of A and B, and they might be connected directly or indirectly. But this one and this one must exist. If that happens in some partial order set, then we will call it lattice. Let's see if any of these diagrams is a lattice. Okay, let's choose let's try to find whether there are pair of elements that do not have greatest lower bound or least upper bound. If we find such a pair of elements, then this is not a lattice. Okay, so help me please, go ahead. Let's start with the first one. Is it a lattice or what? I can see it is a lattice. If we choose any pair of elements, for example, choose D and C, then this E is their least upper bound, and B here is their greatest lower bound. This is the least upper bound, and this is the greatest upper bound of C and D. If we choose E and F, for example, or E and F, okay, so F is their least upper bound and E is their greatest upper bound. Okay, so this is a lattice. Keep trying all pairs of elements. Now let's go to the second diagram. Can we find a pair of elements that do not have least upper bound or greatest lower bound? Can we find? So I'm waiting your answer. If this is not a lattice, then that means there is a pair of elements that does not have least upper bound or greatest lower bound. Can we find one? It looks to me it is a lattice. No, it is not a lattice. What do you think? Not a lattice. Shams, why? Give me a pair of elements. So what do you think, guys? It is a lattice or not? The pair P and C B and C. What is the give me the set of upper bounds of B and C. It is D, E, and F, right? These are upper bounds of B and C. There is no least element among these upper bounds. So the least upper bound of B and C does not exist. So this is not a lattice. Okay, good. What about the third diagram? Is it a lattice or not? The third diagram. To finish this is a lattice. Keep checking, take pairs of elements, and you will always find at least upper bound or greatest lower bound for it. Now, last two examples. Is this set a lattice? Is this set a lattice? It is set of positive integers with division, and the answer shall be yes, because the least upper bound of every two elements is the greatest common divisor, and it must exist. Always exists. Okay, because we are talking about positive integers, not negative. And the greatest lower bound of any of these two elements, greatest lower bound, is simply the least common multiple, and it always exists. So this is a lattice. The answer is yes. What about these? This is not a lattice. This is a set 1, 2, 3, 4, 5 with division. It is not a lattice. We are saying here it is not a lattice. Which element does not have a least upper bound here, or least upper bound of what? Of 2 and 3. Does not belong to S. It's not there if we say this is S. Okay. This is a lattice. While this is a lattice, why? Because the least upper bound for any two elements in here, least upper bound, which is the greatest common divisor, of A, B, this is the set S, always belongs to S. Check this out. The greatest common divisor between any two elements in there is in that set, and the least common multiple, which is the greatest lower bound of any of these two elements, which is the least common multiple of any of these two elements, always belong to S. So the idea here, the least common multiple and the greatest common divisor of any two elements in there are in there. Both of them are in there. So this is a lattice. Good. And this is not a lattice because the least common multiple of two elements, or greatest common divisor of two elements, is not there. The least common multiple actually here. And this brings us to the end. Okay, thank you.